So we'll start the session. So for this, we have two talks. First is by Ariel Amir from Weizmann Institute of Science. So Ariel was supposed to be here. He got his visa and everything, but at last moment he got injured and he couldn't come. So it's a pity. But he has kindly agreed to give an online talk. So Ariel, over to you. And I will alert you like, let's say in 35 minutes.
Okay, perfect.
Okay.
Thanks a lot. Thanks for the invitation. I'm really sorry that due to an unexpected knee injury, I can't be there in person. I'd love to get your questions throughout the talk or after the talk, whatever is better. And so today I'm going to talk about traveling waves in our immune system. And by way of introduction, I should mention that most of the work is my group is actually on slightly different questions, also to do with physical approaches to study biological systems, but typically we study the inner workings of single cells, often bacteria, and the sort of questions relate to how DNA replication is coupled to cell division, how gene expression is coordinated with growth, a lot of stochastic models to study these problems. And if you're interested, we recently published a review on some of these questions. But today's talk is going to be quite different. It's going to be focused on collective rather than single cell behavior, and not on bacteria, but rather on our own immune systems. And so the focus of this talk is on a phenomenon called neutrophil swarming. Neutrophils are the most abundant white blood cells found across species. We have them, and also the zebrafish that I'm shortly going to show you in this video have them. And they're the initial immune responders that respond to a cut. So in this case, it's a laser-inflicted wound in the tail of a zebrafish, but it can also be a response to a fungal or bacterial infection. And what you'll see here are these red cells. These are the neutrophils accumulating over the course of minutes. Time here is in minutes at the site of injury. Okay, and this can also be done in vitro. So this is a study from Daniel Irimea's lab at Harvard Medical School. So it's a microfluidic chip. You insert into it neutrophils from human blood donors, and this is a fungal target. So it's a candida in this case, and you see very similar phenomena that within the course of minutes, the neutrophils accumulate at the fungal infection site. And you can analyze this video by taking cells at a given time and a given distance from the target and asking, are the cells moving randomly around or are they moving radially in? So if I take cosine of the angle with respect with the direction to the center and average that, if it averaged to 0, denoted here by white or light blue, it means cells are just moving randomly. Well, if we get a +1 corresponding to this purple color, it means cells are moving radially in. So in this space and time heat map, this line separating the purple from the white is really the information front. Cells inside this radius know where to go and are moving towards the target, while cells outside are moving randomly. And you can see here there is a time scale separation. The time it takes this information to spread across the field of view is 5 minutes, which is much shorter compared to the several tens of minutes it takes the neutrophils to actually arrive at the target. And this will be useful for the model building I'll show you later on. And we know what the signaling, or one of the main signaling molecules is. It's a molecule called LTB4. And so the traditional picture has been that a neutrophil bumps into the problem, be it a fungal infection or a wound, and starts secreting LTB4. This LTB4 then diffuses away from the target and recruits additional neutrophils to the target site. But there is a problem here, and the problem is diffusion is just not fast enough. We know that the length scale goes as square root of dt, and if we want to recruit neutrophil from a millimeter away, for a diffusion constant for a molecule such as LTB4, you get a very long time of several hours that are inconsistent with what you see in the experiments. Okay, and please stop me if there are any questions. Another way to see that there is a problem here is when you think about the sort of information front you expect from diffusion, length should scale as square root of time, so you expect something concave, while the experiments show something like a time delay followed by an almost ballistic propagation of this information front. So something doesn't add up, and there has to be a different mechanism for recruiting the neutrophils to the injury site. And so several years ago, we proposed that perhaps what's happening is that neutrophils, at the same time that they sense LTB4, not only start moving towards the target up the gradient, but also starts secreting LTB4 themselves, become sources of LTB4, and that could create an outgoing wave of LTB4, and so the signal would propagate much faster linearly in time rather than the square root associated with diffusion. And for the relevant experimental timescales, we expect a wave velocity of several microns per second to get a time of about 10 minutes to cover the distance of a millimeter. All right, so in the next half an hour, I'll give you a brief introduction to reaction diffusion equations. I'll talk about the scaling relations of these information waves with the system dimensionality and other parameters. I'll talk about the perhaps counterintuitive effect of discreteness, the fact that cells are discrete entities. This was the work of a former PhD student at Harvard, Paul Dieterle. And in the last part of the talk, I'll speak about very recent work associated with the self-inhibition properties of these waves. How do these waves stop once they begin to propagate? And this is the work, the theoretical work was done by Deng Pang, who is my current PhD student also at Harvard. Okay, so if you haven't seen this before, it might come to you as a surprise that you can get waves from diffusion, but in fact, this is a long story and with a rich history. And so if we take the diffusion equation, we all know how to solve it. We get this scaling that I mentioned several times. Another famous and simple equation is the equation of logistic growth. If dc to dt goes as c times 1 minus c, I will get initially exponential growth, and then it would saturate to a constant, in this case, 1. And Fisher and Kolmogorov, nearly 100 years ago, as far as I know independently, looked at this equation, which is the diffusion equation supplemented by this nonlinearity. So you can think, for example, about bacteria moving randomly on a surface, but also growing with some finite carrying capacity. And something like this was the initial motivation of Fisher, for instance. And it turns out that if you solve this equation, you get waves. So this is the heat map of the solution. And here is a simple simulation that you can write with a few lines of code. And you see, after an initial transient, you get a ballistic propagation of this wave. And this problem has beautiful mathematics that I won't get into so much today. But there is a famous problem called the selection problem. If you guess a traveling wave ansatz, you will find not only a solution, but an infinite number of solutions. And it turns out the one with a minimal velocity is the relevant one for reasonable initial conditions. Here is an experiment where you look at bacteria growing on a surface, and indeed you see they correspond pretty well to this Fisher wave prediction of a constant velocity of the front. Ignore the fact that there are two colors here. It's not important for what I'm trying to communicate here. And in fact, there are other instances in biology where the combination of diffusion with this nonlinear feedback leads to a propagating wave. So this is one example from nuclear divisions in a developing fruit fly embryo. Sorry, this jumped. So what you have here, you want to synchronize the division of these nuclei, and this is done by a molecule that diffuses, but is also produced by the system in a positive feedback way, and that leads to this beautiful purple waves that propagate across the system and leads to synchronization of the nuclear division. Here is another famous example from a slime mold that is typically single. These are single cells, but under stress, they want to come together to a particular point in space. And so this is done. You'll see here, again, a molecule that diffuses, but through the reaction term, the nonlinear term, similar to the one in the Fisher wave equation, you get these beautiful spiral waves that propagate through the system and ultimately leads to motion of the cells. What you see here are streams of cells until they meet at the center here at this bright spot, the origin of the waves. Here is one final example, courtesy of Alison Sgero. And again, you see the cells will spontaneously start to emit these spiral waves. Okay, these are experiments, these are not simulations. And then the cells start moving, triggered by this, the wave is driving the motion of the cells. This is the signaling information, and they follow the signals and collect at a particular point in space. Okay, so we have a similar problem, and we'd like to model. And so here is the model again for the neutrophils. C of R and T will be the concentration of LTB4 in space and time. LTB4 is obviously going to diffuse, but now the new feature are that cells, when they sense LTB4, they also start to emit LTB4. And so we're going to characterize this emission. A is going to be the maximal emission rate, and F of C is a function governing their emission. So I measure some concentration of LTB4C, and I emit with some function. So you can take here your favorite Hill function or a step function. As I'll show you, the details will be less important. And so I have to sum over, every cell becomes a source. So I have sum over all these delta functions where I is an index characterizing all my cells. And if I take the continuum limit, which I'll get to later on, I'll discuss the conditions under which this will be justified, then we get the equations here on the right, which is similar in spirit to the Fisher wave equation, but with a more general nonlinearity f of c. And we'll see some more, perhaps more important differences later on. Okay, so let's analyze this in the simplest scenario of a spherical symmetry. So let's say I have a system with dimensionality capital N, and if I switch to a radial spherical coordinates and guess a traveling wave ansatz, I will now get an ordinary differential equation that takes the following form. And you see that the only place where dimensionality enters is in this third term here. And you'll notice that it has a similar form to the second term, but there is an extra 1 over r in front of the first derivative. And that tells us something quite intuitive. If I'm far away enough, if I propagated enough, then this term will be negligible. How far is far away? The distance from the target has to be large compared to an emergent length scale that will come up again and again in this talk of d over v, diffusion constant divided by the wave velocity. I still haven't found the wave velocity. I will on the next slide, so bear with me here. But this is a length scale, and when I'm far away compared to that length scale, this third term is negligible, and I basically get a 1D equation. Dimensionality, system dimensionality doesn't enter here. And I think this is intuitive. You know, I'm far away on this curved front. I don't know that the Earth is round. I basically see a flat front. So let's talk about this flat front. And for simplicity, let's assume that f of c is this has this threshold behavior. So I start emitting at the maximal power when I reach when I measure an LTB4 concentration reaching a particular threshold. So now I can easily solve my equation to the front, in front of the wave and at the back of the wave. And you'll find that in front of the wave, I get an exponential decay of the LTB4 concentration. At the back of the wave, I will get this linear dependence. And by matching the conditions, I can find the wave velocity. This is similar to the sort of exercises you'll do in a quantum mechanics course in your undergrad. And this leads us to a velocity that scales as square root of the emission times the density times the diffusion divided by the threshold. And this makes perfect sense. It's a collective effect. So the density of the cell enters, and it turns out it enters in this way. And in fact, you could have reached this conclusion from dimensional consideration alone. We need to construct something that has dimensions of velocity. We're armed with this diffusion and with a threshold divided by emission times density, and that's the correct way to construct a velocity. But in fact, things are not as simple, and the experiments are not done in these conditions. They're done in conditions where cells live on a 2D surface, but the diffusion of LTB4 happens essentially in 3D space. The thickness of the device, of this microfluidic device, is much larger than the relevant length scale, which is this d over v. So for all intents and purposes, this is essentially 2D cells embedded in an infinite 3D medium. And we can solve also that scenario or repeat the same dimensional analysis. So this is the same equation I had before, the same reaction diffusion equation, but now I have an extra delta function in the z direction corresponding to the fact that all my emission is taking place on this surface. And again, diffusion here is full 3D diffusion. And when you analyze this equation, you get a rather surprising conclusion. The velocity of the wave scales as the emission rate times density divided by the threshold. And you'll notice that the thing that is absent from the scaling is the diffusion constant. So in this case, we have waves driven by diffusion, right? Everything is communicated through diffusion of LTB4 from cell to cell, but the propagating wave on the surface has a velocity that is independent of the diffusion constant, which I find quite surprising. Okay, so again, the relevant length scale is d over v. When we take the velocities we see in the experiments of about 2 microns a second and the diffusion constant of LTB4, we get a length scale of about 10 microns. In the experiments, the height of the device is about 1 millimeter, so we're safely in this regime of 2D cells embedded in 3D space. So to summarize so far, I showed you that if the dimension of the cells is the same as the dimension which the LTB4 diffuses in, then we get, regardless of the absolute dimension, this square root scaling on the parameters. If there is a mismatch of 1, like the example I just showed of cells in 2D but diffusion of LTB4 in 3D, we get this different scaling. And in a similar way, we can show that if the mismatch is larger, then the system cannot support any waves. If I had a tube, a 1D tube with cells, but diffusion would happen in 3D, the system would not support traveling wave solutions. We can ask another question. What about the wave initiations? If this is my fungal target and I have a neutrophil outside the target, will it always be triggered by the cells inside the target signaling the LTB4? Or is there maybe a target which is too small for which I will never trigger waves? And so the relevant player here is the green functions of the diffusion equation. And the question is, if we integrate this green function over the target up till a very long time, will I get to the threshold concentration? And for those of you familiar with Polya's theorem, this is very similar to the proof, or at least one of the proofs for Polya's theorem. So I remind you, Polya's theorem is a statement that in 1 or 2 dimension, random walks are recurrent and will always return to the origin with probability 1. But in 3D, there is a finite probability to escape to infinity. And the derivation of this relies on writing the green functions of the diffusion equation in dimension d and asking, does the integral converge or not? And using the same way, we can show that in 1 and 2 dimension, a cell outside the target, no matter how small the target is, will always be triggered, while in 3 dimensions, this is not the case, and there is a critical size below which you will not be able to trigger these waves. What is this critical size? It's again this length scale of d over v. So if the target is too small compared to d over v, you will not trigger waves even if you wait an infinite amount of time. But in 1 or 2 dimension, you can calculate how long you have to wait until this wave will be triggered. So this is the results that are also very dimensional dependent for the triggering of these waves. And maybe this is a good time to stop and ask if there are any questions from the audience. Okay, if not, I'll continue.
So, Ariel, I had
Yeah.
one just clarification. So you
Sure.
had the reaction diffusion equation with just one delta function. So I am trying to understand, was it like a singular point where all the sources have been accumulated? And because
Okay, I get the question. Let me try to clarify. Sorry if this wasn't clear. So I'll get back to this point very shortly, but the real problem we have is that every cell is a source. What I did now is analyze the equation on the right-hand side, where my sources are uniformly spread everywhere. So I assume I have cells with uniform concentration on the surface. And so I replace the sum of delta function by the constant concentration of cells. This is the continuum approximation of the sum of delta functions. I will ask shortly whether this is a valid approach or not. The delta function that appeared later is this delta function corresponding. It's still the continuum approximation. It's not a point source. The whole surface is emitting, but this accounts for the fact that cells are on a surface while diffusion happens in 3D.
I see. Okay.
Okay, and one more point related to your question is that I am not changing the concentration of my neutrophils during the process. Why is that justified? We know that the whole system is designed to get the neutrophils to move inward. Why am I ignoring that? This is where the timescale separation plays in my favor. I can talk about the whole propagation of the wave without worrying about how the cells would later respond and move in response to these waves. We know that the neutrophils move inward, so at later times I will get a non-uniform concentration. I don't need to take it into account at this stage where I'm asking how does the information wave propagate. I hope that point is also clear.
Thanks.
Okay. Any other questions? Okay. So when we look at the experiments, we now understand cells are in 2D, system is in 3D. So this is the relevant equation. Doesn't have to be a theta function. We realize that the scaling will be independent of the particular details of this nonlinearity. And when we analyze the experiment, we understand that there's going to be a delay. This is this initiation until you trigger the waves, the cells outside the target, followed by ballistic propagation at constant velocity. And when we fit the experimental parameters, we get a diffusion constant very consistent with a molecule like LTB4, and we get a threshold very consistent with the properties of the LTB4 receptor. BLT1 is the LTB4 receptors, and it has a dissociation constant very similar to what we infer from analyzing these experiments. It's still not a direct proof of these, what we call diffusion relays, but I'll get to that later in the talk. I want to spend now a couple of minutes asking exactly when can I take this continuum limit? When can I take the sum over the discrete delta function associated with each cell and replace them with this continuum system, the continuum equation? And you will not be surprised that the condition is that cells have to be close enough to each other. How close is close enough? Again, close enough is compared to this length scale of d over v. Okay, but now comes the surprising part, or in a second it'll come. If I analyze this in 1D, I know the scaling of the velocity. This is the square root scaling we derived. And when I look at how far or what the dimensionless parameter that should be small in order for the continuum approximation to hold, it's the distance between cells, d, times v over d. And so we get this scaling, square root of d. The closer cells are, the better the continuum approximation is. This is perfectly in line, I think, with most people's intuition. But when we do the same analysis in 3 dimensions, we find that when we plug in the scaling of the velocity and the distance of between cells, we see that the dimensionless parameter scales as square root of 1 over the distance between cells. What did we conclude? In 3 dimensions, the more dilute my system is, the better the continuum approximation, which to me is quite counterintuitive. In 2 dimensions, we find that the dimensionless parameter is actually independent of the distance between cells. And this is the relevant parameter. So I think the take-home lesson of this slide is we often in this field write reaction diffusion equation like Fisher and Kolmogorov did without checking whether the continuum approximation is a valid one, and you can get surprising results because of the intriguing properties of random walks. This is what's really underlying this flipping of the system is actually takes the continuum approximation at dilute rather than continuum than the dense limits. We've checked this in additional ways. So for example, if we look at waves on an array, periodic array of cells, we can solve exactly for the relation between the threshold velocity and the distance between cells. And we can see indeed when the system behaves like a continuum and when it behaves less like a continuum. And we can see that indeed the dimensionless parameter I had on the previous slide, when it's small, the system behaves like a continuum. The velocity is well approximated by the velocity that we can compute in the continuum limit, while when it's large, we get large discrepancies between these. Okay, so this is, I'm going quickly through it, but this is a summary of how this behaves at different dimensionalities, both of the neutrophils, and we realize we need to care about another dimensionality, the dimensionality of where LTB4 diffuses. We realize that experiments are in this 2D embedded in a 3D space, and when we take the relevant dimensionless parameter for the experimental conditions, we see that luckily we're in the regime where the velocities are well approximated by the continuum approximation velocity. The ratio is close to 1, so everything we did so far was justified. For the experimental conditions, the continuum approximation is an excellent one, but again, the general message is this has to be checked carefully before taking the continuum limit. All right, so in the next few minutes, in the last few minutes, I want to talk about recent experimental work. This is work done in collaboration both with Daniel Iramea's group at Harvard Medical School and also with Orion Weiner's group at UCSF. And inspired by this theory, they set out to check more directly the properties of these traveling waves. So before, I showed you an indirect readout for the waves relying on the motion of the cells. Are cells moving radially in, or are cells jiggling around randomly? And this was an indirect readout because of this timescale separation. We had to wait a long time until we see the cell motion. And what they developed here is a way to more directly visualize this wave using something called calcium imaging. So what you need to know for the purpose of this talk is that when cells sense LTB4 and start, according to the model, participating in this relay, they also release intracellular calcium, and this can be measured directly using video microscopy. So now we have a direct readout. Even before the cells are starting to move, we know our cells starting to secrete LTB4 and participate in this relay. So what you see here in this video, you will see 4 fungal targets, just like before, but now we're measuring in purple, this is the readout, our cells, in yellow, whether cells are participating in the relay. And I hope you can see these beautiful rings emanating from each of these 4 targets. Okay, so these are now direct evidence for these propagating waves. And now we're going to analyze them. And again, the big improvement is because cell velocity is much smaller than the wave velocity, here we don't need to wait for the cells to move, and we can already see the information waves propagating. So the first thing we did was validate that this is indeed what we think it is. So what you can see here is the propagating waves as imaged using this calcium imaging, and you can analyze whether cells inside and outside have different properties. And indeed, you see that the cells inside are moving radially in, while the cells outside are just jiggling around randomly with essentially zero mean radial velocity. And you can indeed see again that the speed of the traveling wave is an order of magnitude faster compared to the speed at which cells are starting to migrate inwards in response to these waves. Okay, so this is validating this calcium imaging as a good readout for the chemotactic motion, the motion of cells towards the center. Now, we want to really see that this is a relay. And what is the smoking gun for a relay? The wavefront distance, r squared, should scale as time squared because it's a ballistic propagation. Well, if we had just a simple model I outlined at the beginning where it's just diffusion of a molecule, then just like diffusion, r squared should scale linearly in time. So the smoking gun is an exponent of 2 rather than an exponent of 1. Now, Feynman has a famous quote, "What I cannot create, I do not understand." And I'm going to flip it on its end and say, "What I cannot break, I do not understand." So if there is really a relay with an exponent of 2, how will I be able to break the relay? I can block the LTB4 receptor with a drug. So there are known drugs that block the LTB4 receptors. If we block them, we should go back to normal diffusion. And so this is how it looks like on a particular experiment. If you take blood from a donor, you get an exponent very close to 2. If you add the drug, you get an exponent that becomes much smaller and close to 1. If you average over many experiments, we find that an exponent of 2.2 becomes an exponent of 1.1. Very consistent with a relay being destroyed. Here is how it looks like on a video. On the left, you see the normal blood, and on the right, you see what happens when you add this drug. So on the left, you see these beautiful waves exploding from the center, and on the right, you see a fizzling response that looks much like diffusion. And you can see that also in the normal case, the cells manage to move in collectively to do this neutrophil swarming very efficiently, while on the right, also the neutrophil swarming is impaired because, again, the information cannot travel as efficiently. Now, so far I discussed waves that once they initiate, never stop. And this is the case within Fisher waves and with, in general, with reaction diffusion equation. But what we realized that for the immune system, stopping is a must. If I have a small cut on my forearm, I don't want to recruit all the neutrophils from my body to this small injury. So I must have a system that once waves propagate has a finite extension, and then the waves would stop. And we asked ourselves, how can we do that? Can we construct and test models of waves that have a finite extension? And so this was the work of Deng Pan, a PhD student at Harvard, and Dr. Wencheng Ji, my postdoc at the Weizmann Institute. And after a lot of dead ends, we realized that this system, this simple model can do exactly that. So what do we have here? L here is the LTB4. Just like before, it diffuses, and this theta function accounts for the fact that above a given threshold, I will start secreting LTB4 and create this diffusive relay. But now I have an extra theta function that when I reach a threshold of another molecule, R is an inhibitor of LTB4, it will shut off my LTB4 propagation. What creates this inhibitor R? The LTB4 itself. So when I reach a low level of LTB4, L1 is actually lower than L0. Even before I start secreting LTB4, the first thing I start doing is producing an inhibitor that will ultimately shut off the system and stop the propagation of the waves. And you'll notice that this inhibitor, I didn't add a diffusion constant. This is because we think we know what the identity of the inhibitor is, and unlike LTB4, it's intracellular. So cells are creating this inhibitor in an intracellular fashion. So how would this look like? If you look on the right, you'll see LTB4 propagating, and then very abruptly, this is the blue, shutting off. Okay, this is what you see both on the left and the right are simulation of the equation I had on the previous slide. There is a parameter regime in which you get persistent waves that never stop, but in the right parameter regime, the system can support traveling waves. The video is looping. You can see the LTB4 is propagating and then very abruptly being shut off by the inhibitor that build up. This is how it looks like. Sorry? Was there a question? Okay. This is how it looks like in 2 dimensions. So again, you see the LTB4 building and then being chewed up at the back by the inhibitor that ultimately catches up with it and switches the wave off. So the wave propagates, the inhibitor starts building up, catches up, and shuts everything off. I told you before, one has to check the discrete case before jumping to the continuum limit. Here is a simulation, agent-based simulation with discrete agents rather than the continuum one you have on the left. And you see basically the same phenomenology. We understand the analytic criterion for when the system has persistent waves and when it has these self.
You have like another 5 minutes or so.
No problem. I'll finish in 5 minutes. No problem. Thanks. And please, if there are any questions, feel free to stop me. So when do we get waves that propagate forever? That happens when the point at which the inhibitor reaches a threshold is far enough behind the propagating wavefront. How far is far enough? Again, this D over V length scale that appeared multiple times during this talk appears. So when this point is too far behind the front, you get persistent waves that the inhibitor is not able to catch up. Okay. The discrete simulations, as I mentioned, recover the continuum modeling results, and the model captures well the shapes and dynamics that we see in the experiments. But like I said before, the real proof of this model is if we can break it. So if this is really the mechanism of the self-extinguishing nature of these waves, that there is this inhibitor, we should be able to target it and destroy it. So in this case, based on the biological literature, NADPH oxidase was a known inhibitor of LTB4, and luckily there is a drug that suppresses it. So what do we expect? We expect that when we add this drug, DPI, there will be no inhibitor, and without an inhibitor, we should get waves that propagate basically forever. And this is indeed what we see. So while this is the case of blood from normal donors without the drug, and you can see that the waves propagate and then stop, when we add this DPI, you will see waves that basically continue throughout the field of view without stopping. And in fact, there is a disease called CGD, chronic granuloma disease, which where neutrophil swarming is impaired, and it's in this disease, it's exactly this inhibitor that is affected. And when we tested blood from patients with CGD, we get essentially the same phenomenology you get when you add this DPI. Okay, so you get waves that basically don't stop, as the model predicts. And with that, I'll summarize. So I showed you here that diffusive relays allow cells to respond rapidly, going beyond the limitations of diffusion, and with strong gradients. I didn't talk about it so much, but you can imagine the gradients that cells would see at the front of the wave when the waves reaches them are much larger than the Gaussian, than the Gaussian green function of the diffusion equation predicts. I showed you a strong dependence on the system dimensionality, and in particular, the wave velocity depends on the dimensionality difference, the difference between the dimension the cells live in and the dimension diffusion happens in. I showed you counterintuitive results for the validity of the continuum approximation, where in 3D, the more dense the system is, the worse the continuum approximation is, unlike our typical expectations. And I showed you a new model for self-extinguishing waves with testable predictions. This was for me a nice example of experiments by Daniel Irimea that motivated our theory by Paul Dieterle, that motivated experiments by Orion Weiner's group, and in particular, fantastic students, Evelyn Strickland, which in turn motivated our next generation of theory by my students, Deng and Wencheng. And in addition, this work led to these remarkable videos that, at least to me, remind of actual fireworks. And with that, I'm going to stop and take any questions you might have.
Okay, let's thank Ariel for this very nice talk. So, are there questions? Comments? Okay, so Ariel, I was just wondering, like, can you actually create like random walk-based model, especially for the relay wave kind of thing that you showed, right? So, because it's much more easier probably to create this kind of extinguishing waves or putting boundary conditions with random walks, right?
It's not clear to me if you're referring in this throughout the talk. LTB4 does a random walk, right? That's the only thing LTB4 can do, because it just follows the diffusion. So are you talking about random walk of the cells?
Right. No, I can see that these are wave equations, like diffusion equations, but I was just more interested in whether you can actually create microscopic random walk which will give rise to this continuous limit, coarse-grained limit.
Absolutely. So, in a sense, we know from the days of Einstein that this is synonymous, so we can talk about the diffusion. In this case, it's more efficient to think about diffusion of LTB4, because we know LTB4 is going to be a very high concentration, many copy numbers. So I don't need to care about the individual random walk of a particular LTB4 molecule. I know it's going to be characterized well by a diffusion equation, but I do have to account for the sources. The cells become sources of LTB4.
I was wondering about how can we incorporate the source term via random walk models? Is it possible?
So in this case, the sources, the cells, are not just doing a random walk because they're beginning to chemotact. So far, I didn't account for the motion of the cells. I assumed constant concentration of my sources, which was not changed. Something that we're currently working on is putting in the cell motility into account. It's not going to be a simple random walk, because we know cells, once the wave passes through them, start to move radially in towards the target. So that will be maybe a biased random walk. We think it's a bit more complicated than that too, because we know that cells, basically for every wave that travels through the system, the cells move a little bit. They don't continuously move toward the target. And we're beginning to put this information into the model. And now we'll have not just the equation for the LTB4 and the inhibitor, but also a field, another equation for the density field that will change in time.
So the reason actually why I asked this question, because you can have mortal random walker which will die off after some certain rate or after some stochastic times, and that may just make this self-destructing waves that you were showing. So that was just like a comment I wanted to have. Okay. Any other questions? Comments from the audience? If not, maybe let's thank Ariel again. Ariel, thank you very much for giving the talk, and I hope in future you will have time to come here in person.
I hope so. Thank you very much. Enjoy the conference. Bye-bye.
Bye-bye.